Hey everyone, welcome back to physics. Hopefully the test went okay. I'll get those back to you soon. Today we start a new unit called waves, and waves is a super fun unit. Waves are a part of physics that we have not explored yet that are very interesting, that are not so obvious. Things that are happening in it are just amazing, and they're happening around us, and we can test them and see that they are happening, but we can't really see what's happening because waves are just weird and they're not visible all the time. And so we're going to start with waves in one dimension. Obviously, waves are more than one dimension. They're three dimensions or more in the real world. And of course, we got to start simple. So you've learned a little bit about waves probably in grade 8 when you talked about light. So if you remember learning about light and how it bends and you can make a rainbow, that's waves. You learn about the electromagnetic spectrum. Those are waves. The light that we see are just light waves that are bouncing back, that are reflected. So for example, white, when you see something that is white, it is reflecting all of the light, all of the colors of light back at you, and so you see white. When you see something that is black, it reflects none of the light colors back at you, and so you see black. When you see blue, what's fascinating is you're seeing all of the colors, only all the colors are staying there except for blue. Blue is what is being reflected back to your eye. So a blue thing is everything but blue. It absorbs everything except blue light. So it's just interesting. So we observe, we live in a world full of waves, and yet we don't really know what they are. And so let's start learning about them. What is a wave? A wave is a disturbance that transfers energy, not matter, from one place to another. So we'll look into this right away. A mechanical wave is something that needs a medium to work in. And what is a medium? Okay, a medium is just the material through which the energy is transferred. Okay, so sound waves, the medium is the air around us. Okay, if you try talking underwater, I do this with my son lately. It travels differently. It sounds different. The medium is different, and so the wave, the way it travels, is different. Water waves. When you splash someone in water, the water is the medium, right? That makes sense. Electromagnetic waves don't require a medium. So when we talk about light, like I was just talking about, light doesn't require a medium, right? It just shines. So to the point, sound waves need a medium. That's why we don't hear the sun. If there was an atmosphere, we would hear the sun all the time. It'd be tremendously loud. It'd be like a hair dryer beside your ear all the time. Super annoying. So good thing there's no air particles, but we still get light from the sun, which means light doesn't need a medium. Okay, it travels through empty space, through the vacuum of space. So radio waves, microwaves, they don't need mediums, right? Microwaves need electricity. Radio waves don't. Microwaves are actually a thing besides what you heat your food with. Here's an awesome video. Watch this. 109,000 people doing the wave. If we're going to learn about waves, we've got to understand the wave. Now, this is just epic. This was 2 days ago. Just kidding. Social distancing, man, this just looks terrifying, does it not? These people are all going to get sick. But that is one tremendous wave. That's insane. 100,000 people. What is there? 700,000 people in Winnipeg? That's insane. So you see this wave coming around, and I'll ask you the question. What are these people moving around the circle? What are they moving around the circle? Are they passing something? No, they're not moving anything around the circle, right? But watch, you can see something going around the circle. You can see something moving through the crowd. And what is that? It's It's nothing. It's something. And all it is energy. And so in this case, their energy is moving around and like nothing's forcing it except for that the people are choosing to continue. But this is all a wave is. The other thing I want you to notice is these people. Are the people themselves moving? They're just going up and down. And by going up and down, which direction is the wave moving? Right to left. This is a very bizarre thing. And this is how waves work. And often when we think of waves, we think, oh, well, the wave is moving things forward. It's not. The wave is moving up and down. And then the energy gets transferred along. And that's pretty crazy. So this that we just watched is a transverse wave. Okay? This is next in your notes. The direction of a particle movement is perpendicular to the direction of the pulse. And so the medium particle, okay, in this case it was a human, but even if you did this on a string or even in water, okay, you'll see that the particle motion goes up and then goes down, like the person doing the wave stands up, sits down, and that is the wave. And what direction is it? It is perpendicular, the other direction, going to the side, right? So you go up and down, and the pulse goes forward. Weird, right? And so this is called a transverse wave. A periodic, oh, right, I was going to do another slide here. Sorry, I just got into this too quickly. Get it up here. Got too much going on. Okay, here is an example of a wave. Poof, right? You do this all the time. I can think of doing this with skipping ropes, long extension cords that were stuck on scaffolding. It's just kind of do a little pulse with, right? So you push it up and down and the wave travels along. You can look at the green dot, right? It just goes up and down, and yet there's this energy that is moved along this string. Okay, fascinating. That was wonderful. Present. I don't know, where does this start? Good. Okay, periodic transverse waves. So it's still a transverse wave, but it's periodic. So the word periodic means continuously moving or oscillating. Oscillating means turning almost, right? Like a constant motion. And so, for example, a hand oscillating a rope or a spring. Okay, so when you're doing skip rope, your hand is oscillating. Okay, sound waves from a speaker, it is oscillating because it's going back and forth constantly. Okay, and so we can change what I just worked with here. Wow. To oscillate, and you see this is oscillating wave. Oh, that's satisfying. Okay, this is a periodic wave. And you can see there's a wave, there's another wave, another wave, another wave, another wave, another. Okay, you get the point. And you still watch these green ones, and they're just going up and down, right? You watch in slow motion, it just goes up and down and up and down. And I know what you're all thinking, boy, I hope we get to play with this site. And you will yet. It's not part of today's, but this is coming. It is coming. And if you have a Slinky at home, you can also play with Slinkies. If you don't, I will make it possible for you to pick a Slinky up at school. And if you want to drop by the school sometime next week, pick up a Slinky. I'll get them ready for you there. But I'll give you more details on that later. Okay, very cool. This is beautiful to watch as it goes up and down. This is called a periodic wave because a new wave comes periodically, okay, every so often. Okay, so here are the parts of a wave, specifically a periodic transverse wave. So transverse wave means it's physical. It's up and down, right? It's something that's waving like that, like you would wave a string, right? Here are the parts. There is the middle position. It's called the equilibrium position. It is right down the middle. Everything has it. All these periodic waves have it. There's a crest, which is at the top. Okay, the crest is the top, and the bottom is called the trough. It's not trough. This is how you spell that. It's Like if I was writing it on the board, you wouldn't believe me, but this is in text. So now you should believe me. There's the crest and the trough. Halfway between the crest and the trough, that's where the equilibrium position should go. Okay? It is halfway, which means from the crest to the equilibrium position or from the trough to the equilibrium position is the amplitude. Okay? Now it's important, if you go from crest to trough, that's 2 amplitudes, right? So the amplitude of the wave is from the equilibrium to the crest or the equilibrium to the trough. But generally, I just go with this one. Very good. You will see this if you've ever done any music work on and editing on software. You will see waves, sound waves that you're working with, and you're working with all this stuff. The larger the amplitude, the louder the volume often. So they use that. The next thing is wavelength. The way we measure the wavelength is from crest to crest or trough to trough. That's the easiest way to do it. So from one crest to the next crest. If we go from equilibrium position to equilibrium position, if you look here, we've got to from one equilibrium position to the next one. It is not a full cycle yet. It is not repeating. It was going up, down. It's still going down, and it actually takes till 2. So from here, this is one wavelength. Okay, so you've got to kind of watch for that. It's going up, and here it repeats. So that's why we generally don't measure using this, because then we got to be more careful. It's easier to go crest to crest. That is a wavelength. A wavelength is how long does it take before it is repeating itself, before the wave is repeating. That's a wavelength. So trough to trough also works. So just definitions of these things. A cycle is when it completes one up and down movement and back, once it's repeating itself. That's one cycle. The wavelength is the horizontal length of one cycle, and I would just call it the distance from crest to crest. And so if we do crest to next trough, that's just half. The frequency, the number of cycles per second measured in hertz. This is a new unit, hertz. You might think another one, wow, that hurts. But there's more to come. 1 hertz is 1 per second, whatever that means. It's just how many cycles per second. And so whenever you're creating a formula for this, or say that I say there's 7 waves in 6 seconds, you just put the seconds on the bottom and you go the frequency. Okay, 7 waves, 6 seconds, 7 divided by 6. Put the seconds on the bottom. Okay, period is the length of time for one cycle to complete. So it's actually it's related to frequency. Excuse me. It's related to frequency, but it's measured in seconds. It's actually the inverse of it. Okay, how long for one cycle to complete? So a period, how long does it take for this next wave to come after the first wave came, right? How long till it repeats itself? And that's measured in seconds. So if you have the period t, if you have the frequency, you go 1 divided by the frequency, you get the period. Or if you have the period and you go 1 divided by the period, you get the frequency. So that's kind of nice. We'll do a question with that right away. The amplitude, like we said, maximum height. Okay, and so it's the distance from the top of the crest to the equilibrium position. If you go from crest to trough, that's double amplitude, so be careful. And the wave velocity is how fast the wave is moving. Okay, and so it's the speed of the wave pulse. It's not the speed of the particles going up and down. We don't measure that. We just measure how fast the pulse is moving along. Okay, something with frequency and period. If you're walking down the beach, you're missing good old days of quarantine because you're on the beach. That's pretty sweet. I was just wondering that. Is the beach going to be closed? I don't know. That's weird. Can you go to the lake? Hopefully. Anyways, you count 23 waves run over your feet over a time of 52 seconds. And of course, you're thinking about physics. And so you're thinking 23 waves, 52 seconds. The period, how long each wave takes, you do the seconds on top and then divided by how many waves. So 52 seconds for 23 waves, that's 2.3 seconds per wave. Okay? You got a new wave coming every 2.3 seconds. You found the period. If you want the frequency, then you can just do how many waves per second in one, right? So not how many seconds per wave. This is waves per second. So there's 23 waves, 52 seconds. So it's 0.44 waves per second. So in 1 second, you'll experience 0.44 of the wave, right? That's hertz. Hertz means per second, all right? Heinrich Hertz is the one who came up with that, worked with waves. So just a quick note, if you do 1 divided by 0.44, take 1, so the inverse of that, 1 divided by that, you get 2.3. Okay, so you can go back and forth between these two. Longitudinal waves are a different kind of waves, okay? So we've learned about transverse, those are the ones going up and down. The particles in longitudinal waves don't go up and down, they go in the same direction as the wave, okay? And they look like this, like a slinky. If you tighten it up and just release a bit of it, okay, it's going to create this kind of pulse. Sound travels this way, okay? We will have lots more examples of these, but today we're just getting some definitions out of the way. So longitudinal waves, however you want to say it, say that a wave is moving this way, okay? So this pulse here is going to keep moving and eventually be there, and a new one's going to come. The direction of the particles in this are going to go there and then back, and then there and then back, okay? And we call this part, so these compressed parts are called a compression, and because they're compressed, and in between, it's rare to see any particles, so we call it rarefaction. That's a great word, rarefaction. And finally, you've been wondering when we got to use a word that was that cool, and there it is. It's rare that we get such a cool word in physics. And a wavelength, we still have a wavelength that's between compressions or between rarefactions, but we kind of avoid anything with rarefaction. So compression is area where the particles, of the medium are close together, and the rarefaction are areas where the particles are far apart. Quick demo of longitudinal waves. Okay, so you see the wave pulses moving forward, and this particle is in red here, is just moving back and forth. And look at any of these particles, and they're just moving back and forth, creating this wave. So these are longitudinal waves. Okay. Water waves would kind of act like that, right? Water waves are kind of a combination of both. But still, the particles are not moving all the way along. Particles are just moving back and forth, right? They're not the pulse. They create a pulse, but they're not the pulse. So waves just transfer energy along, and they're not moving particles, they're moving energy. Very interesting. So wavelength is the difference between the two rarefactions. A quick formula that you can write down that we will use. The velocity of the wave can be found. So velocity is how fast that pulse is moving along. It is lambda divided by t or lambda times f. Either of these work. Okay, so if you have the period, use this formula. If you have the frequency, use this formula. Okay, these will both get you the same thing. And v is velocity. Lambda is the wavelength. Okay, this is the new one. Lambda is the wavelength. This is a lambda, just so you know. And f is frequency, and t is period. So a wavelength is how long the distance between the two peaks. At any point, you can pause and go back. It's a nice thing. So a wave is in a pool and has a wavelength. That's lambda, 2 meters, period, big T, 3 seconds, in terms of velocity. So we're going to use this formula, V equals lambda over T. In this case, lambda was 2 meters, period was 3 seconds, and so we get our velocity of our wave. Pretty simple. And next question, red light has a wavelength of 635 nanometers. Remember the back of your formula sheet. Nanometers is times 10 to the negative 9. Okay, so this is red light. Has that kind of wavelength. Speed of light is 3 times 10 to the 8 meters per second. Okay, so we've got V and we've got lambda. So what is the frequency of red light? 3e8, that means 3 times 10 to the 8. That big E on your calculator, right? Handy tool. 635e negative 9. Nano means to the negative 9 times 10 to the negative 9. And we find a frequency of 4.7 times 10 to the 14 hertz. Very quick. Okay. Frequency is how many waves per second. Okay. 4.7 times 10 to the 14 waves per second. cycles per second. Very good. So that's it. For today, beyond this, I've given a Kahoot just to go over the terms and definitions. And I think Monday will be just let's really get used to. I'll give a few more examples of waves, and I'll just be getting used to the terms because we really got to be comfortable. This is new language we're using, right? Frequency, and then understanding amplitude, wavelength, period, cycle, all those things. We have to get used to these terms, and so Monday is going to be just getting used to terms, and then coming to terms with the fact that we're learning about waves at home, just for fun. Okay. Well, have a great rest of your day. It's been fun, and I look forward to seeing how you do on the Kahoot. Have fun.